So welcome everybody again for the second part of the seminar. Today, Mariel Supina is going to continue talking about the universal valuation of Coxeter Metroid.
Great. Yeah, cool. So yeah, apologies if some of the slides look very familiar from 10 minutes ago, but so I defined in the pre-seminar a bunch of sort of families of polytopes and concepts that will come into the talk. So just to, okay. Oh yeah, okay. So this talk, I'll talk about some work that I did with Chris Ure and Mario Sanchez, and it resulted in a paper which has the same title as the title of the talk. So if you're interested in that. And so I'll start by kind of recapping the definition of evaluation and saying a little bit more about what I mean by a universal valuation, and then I'll get into some of our results. So. Yeah, okay, so this slide was the same as before, but basically there's two different ways you can think of valuations, and they're not entirely the same. I think this one is a little bit more specific, I think. Sorry, now I'm getting all mixed up. But anyway, this definition is called weak valuations, and this definition is kind of the one that you can think of. At least this is the one that's easier for my brain to understand. So if I have a family of polyhedra P living in some vector space, then I can say that a valuation is going to be a function that takes in some polyhedra and has values in an abelian group that has this property where I can evaluate my function I can evaluate f on P by subdividing P and then evaluating f on all of the faces of the subdivision and doing inclusion exclusion. So this is an interesting thing to study because a lot of different invariants and like functions on families of polytopes that people are often interested in have this nice property. So as I said before, there's sort of an alternative way to talk about it, and this one's called strong valuation. And this one is the one that all of our work used, I guess. But okay. So for this definition, we say that we can construct the indicator module for the family of polyhedra. So for each polyhedron, we can take the indicator function that evaluates to 1 if some vector is in my polyhedron and 0 otherwise. I can take the Z module generated by all of these indicator functions. And then we say that a function is a valuation if there exists some Z-linear map F tilde on the indicator module such that F of P is the same as F tilde of the indicator function of P. And so this is related to the previous definition because this indicator module has this nice kind of inclusion-exclusion property that I was describing before in the more geometric definition. So I said this definition was the commutative diagram version. So now here's an actual commutative diagram as promised. So this one is just what it means to be a valuation. So if I have my family script P in the upper left, I have F going to an abelian group. So F being a valuation means that evaluating F is the same as sending each polyhedron P to its indicator function and then applying some Z-linear map F tilde on the indicator module. So in other words, valuations are in some sense the same as Z-linear functions on the indicator module. So this diagram says what it means to be a valuation. So my work was about universal valuations. So now I want to show you what I mean by that and kind of formulate the question more concretely of what it means to find a universal valuation for some family of polyhedra. So here's a bigger commutative diagram. So here on the lower left, I have that same diagram from before. So that part is just what it means to be a valuation. And now I want to construct some universal valuation. And so universal means that it should be a valuation where for any valuation f, there exists a unique phi such that f is phi composed with the universal valuation. In other words, it's kind of like the most general valuation I can get, where every other valuation is like a special case of this. So how can we construct the universal valuation? Well, I said that having a valuation is kind of the same in some sense as having a z-linear function on the indicator module. But to define a z-linear function, on some z module, all you need to do is find a basis and then assign a value to each basis element, and that completely determines your z-linear function. So it turns out that the problem of finding a universal valuation reduces to finding a basis for the indicator module. And once I have that, then I can write down a universal valuation as the function that takes in a polyhedron P. It sends it to its indicator function, and then it kind of writes out the indicator function in terms of some basis for the indicator module. And so that's what I mean by finding a universal valuation. And then this function, this unique phi that sends the universal valuation, or that composes with the universal valuation to give you f, will just be the function that assigns the appropriate thing to each basis element for the indicator functions. So this is kind of the problem that we're looking at. And it turns out that in general, if you have just any family of polyhedra, finding a basis for the indicator functions can be pretty hard. But if we have some nice families, such as generalized pernitahedra or matroids, then we can describe a basis, and that lets us write down a universal valuation. So this is kind of like the problem that I'm looking at. Are there any questions so far about that?
So I had a slight question. I'm sorry, it's a bit difficult to phrase. I'm wondering, the universal valuation, does it depend on the abelian group, or is it universal for any possible choice of group as well?
I think it should be universal, yeah, no matter the codomain of the function, yeah. Because I can make my unique function phi go into whatever abelian group I want, yeah. So,
Okay.
Yeah. So it's not the universal, yeah. So the universal valuation, at least in the sense I'm talking about, it's not. It's unique up to isomorphism, I guess. So, yeah, because it's unique up to like a change of basis for the indicator module. So.
No, I was only asking it because you mentioned the relation with the Tat polynomials, and like a lot of the statistics are specializations of the Tat polynomials. That's why I was thinking whether you also have to worry about which abelian group you're going to be. You have parameters in your image.
I see. Yeah, I don't think you need to worry about that. Yeah.
Thanks.
Okay. Okay, so this is what I talked about before, but so our first result that I want to talk about has to do with the case where my family is just the family of deformations of some polytope. So I have any polytope Q, and I take my script P to be like all the deformations, where a deformation is what I get by taking Q and sort of like translating the facet defining hyperplanes along their normals, so that in like allowable ways, I guess. So this I mentioned in the pre-seminar. So in order to say what the universal valuation for a family of deformations is, I need to give you like two more definitions by picture. So the first one I want to give is the definition of the tangent cone of a polytope at a face. So here, yeah, so just verbally, this cone is going to be the cone generated by all of the edge directions of the polytope that are emanating from that face. So for example, if my polytope is this hexagon and my face is this vertex V, then the tangent cone is going to be the cone generated by the two edges that are sort of pointing out from that vertex, and it'll be this pink cone CV, and it's positioned at the origin. So it's just, it's always going to be contain the origin. And if I take on the right, if I have the same polytope, but my face is this edge F now, then I'm going to get the cone that's generated by both the edges that sort of touch F with one of their endpoints, as well as the two possible orientations of F. And that will give me this half space CF. So that's going to be the definition of the tangent cone of a polytope at a face. And this is kind of related to the previous slide because the tangent cone is always going to be a deformation of the polytope. So then the second definition I want to give is that of tight containment of a polyhedron in a cone. And so this tight containment is when a polyhedron is contained in a cone and it has non-empty intersection with the lineality space, the lowest dimensional face. So on the left, we have two examples of this. So you can see that the hexagon is contained in this pointed cone and it touches the point of the cone. So that is tightly contained. And then also the triangle, the blue triangle is contained in this half space and it intersects the line, the lineality space. And so both of these are examples of tight containment. And then on the right, these are not examples of tight containment because even though both of both this yellow hexagon and the yellow triangle are contained in the cones, neither of them touch the point of the cone. And so those are not tightly contained. And so this is also kind of related to the previous definition because if I have the tangent cone of a polytope at some face, I can always take the tangent cone and I can translate it so that it's positioned at that face instead of the origin. And then the polytope will be tightly contained and it's in this translation of its tangent cone. So for example, if I take CV and I just add V to it, so the origin is at V, then I get the hexagon tightly contained in that translation. And so with these two concepts, I can now say our first result. So our first result is that, so remember, if we want to find a universal valuation for the family of deformations, I need to find a basis for the Z module of indicator functions of these deformations. And so our first result is that if Q is the special polytope that I'm deforming, then the translations of tangent cones of Q form a basis for the indicator module. So here, so the C's in this set are the tangent cones of Q at all of the different faces, and V is just any point in your vector space. So this is a very, very large basis, but it is a basis. And so then as a corollary to that, just from what I was saying before, we get that the universal valuation for the deformations of Q is given by taking basically a formal sum over all translations of tangent cones of Q that tightly contain your polytope P that you're evaluating the function at. And I'll do an example of this in a few slides, and then hopefully this will be a little clearer. But so this is our first result about how to get the universal valuation. And I do want to make a note that even though I said the universal valuation is taking the indicator function of P and writing it out in terms of a basis, there's actually kind of like a sneaky change of basis happening between the proposition and the theorem on this slide. So I am writing it out in terms of a basis, but it's not the basis that I had in the previous proposition. I just wanted to make a note of that for the example later. So I'll point out where this comes into play. But we just chose to write the universal valuation this way because it looks a little bit nicer. So that's our first result. And then so just to recap what I said in the pre-seminar, so we can apply this to very special families of deformations where now our polytope Q that we're deforming is the standard permutahedron in type A, or in a general Coxeter setting, it would be a Coxeter permutahedron, which is the convex hull of the reflection group orbit of some generic point, where phi is a root system and W is the reflection group associated to that root system. And your generic point is just a point that's not fixed by any of the reflections in your reflection group. So if that's my phi permutahedron, then deformations of that are what I'm calling generalized Coxeter permutahedra. And so given this definition, our previous results can like immediately apply to this family. And we can say that the universal valuation for generalized Coxeter permutahedra is given by a formal sum over all translated tangent cones of the standard Coxeter permutahedron that tightly contain your polytope.
Sorry, I have a question. So when you, in this sum, V is a vertex of P or
it's just any vector, in the vector space, yeah. But we'll see that like you'll only need certain vectors. Yeah, well, there's an example right here, I guess. Yeah, so this sum ends up being finite. And yeah, so for this results, I just want to mention, like in type A, this was proven by Dirksen and Fink for generalized permutahedra, and then Chris and Mario and I generalized this to deformations in general, as I just said, and then applied that to get generalized Coxeter permutahedra. So here's an example. So if P is this triangle is a generalized permutahedron. It's a deformation of the permutahedron pi3, the hexagon. And so I said that the universal valuation will be the sum over all translated tangent codes of the hexagon that tightly contain my triangle. So here, so there's 13 tangent codes of the hexagon. There's one for each of the 6 vertices. That's going to be like the top row in the sum. And then there's one for each of the 6 edges, which is the first part of the bottom row of the sum. And then there's the tangent cone of the whole hexagon, which is just the whole space, and that's the last term. And so for each of these tangent cones of the hexagon, there's exactly one vector V that I can translate it by. Sorry, not exactly one vector V, but there's exactly one sort of translation of the cone that that makes it so that my triangle is tightly contained in that cone. And so that's why I drew the triangle inside each of the cones, just so you can see like how the cone would need to be translated in order for the triangle to be tightly contained. So yeah, so the top row is all the ways the triangle would be tightly contained in the 6 vertex tangent cones at the vertices of the hexagon. And then you have the 6 tangent cones at the edges, and then the whole thing. And so just to refer back to the comment I made earlier, so I said that I'm just taking the indicator function of the triangle and I'm writing it out in terms of a basis, but you can see from here that it's not actually true that the indicator function of the triangle on the left is the sum of the indicator functions of the cones on the right. You can see that because if I have a point in the triangle, it'll evaluate to 1 for the indicator function of the triangle, but it'll be in all of these codes on the right-hand side and evaluate to 13. And that's just because there was like a change of basis happening, an upper triangular change of basis happening in between those 2 statements that I made. So this is written in terms of a basis, but it's just like a slightly different basis. So yeah, so this is what our universal valuation looks like for generalized permutahedra. Any questions before I go on to Natroids?
So for example, say for volume is one of the valuations, and say for permutahedra, is it like there's some formula, like formulas where you sum over vertices and you look at cones? Is that so? What would happen is that in the valuation, a bunch of terms are 0, for example, or
yeah, exactly. So when you compose it with this function phi that like gets you, that assigns the correct value to each basis element, it'll end up having to be 0 on the non-vertex cones. Yeah. I see something in the chat. Is it known how many terms? Yeah, it'll be the number of faces of the permutahedron, of the whatever permutahedron you're deforming. I think, yeah, there'll just be one term for each of those. Yeah. Okay, so let me move on to Natroids. So now, so now just going back to type A, so just the symmetric group, the edge directions EI minus EJ, forgetting about the Coxeter stuff for a second. I'm going to define Matroids as a family of polytopes, which is like one of the many, many ways to define Matroids. And so the reason people care about Matroids are because they generalize, well, one reason are because they generalize this notion of linear independence. And they end up being a subfamily of generalized permutahedra. So they're not themselves like an entire family of deformations of something, but they can all be obtained as deformations of the permutahedron. And so we say that a matroid is a polytope with edge directions of the form EI minus EJ and vertices that are 0, 1 vectors. So in other words, I'm just taking the definition of generalized permutahedra and I'm also requiring certain types of vertices, and that gives me matroids. So for example, if I have this, I can have this pyramid here where these are the 5 vertices. They're all 0, 1 vectors. And if you subtract any 2 adjacent ones, you will see that the difference gives you EI minus EJ, something of that form. And we also say, so one thing you'll notice is that each of these, in this example, each of these vertices has the same number of 0s and 1s. And so we say the number of 1s, we call that the rank of the matroid. So here it has rank 2. So if you're familiar with matroids in some other definition, then what you can think of is here, I'm taking all of the bases of the matroid and I'm taking the indicator vectors of them, and those give me the vertices of this polytope, the matroid polytope. So here the bases would be from the top vertex, you would have the basis 1, 2, and then on the bottom you'd have like 1, 3, 2, 3, 2, 4, and 1, 4. So this is my definition of matroids for this talk. And in particular, for each dimension and each rank, we have a very special matroid called the uniform matroid of that rank. And that's going to be what I get when I take, so if my rank is R, then I'm going to take all of the 0, 1 vectors with R1s and N minus R zeros, and that gives me the uniform matroid, URN. So for example, U24 gives me this octahedron, and you can see that the matroid from the previous slide is like the top half of that. And in general, it's true that all matroids of rank R will be contained in the uniform matroid in this way, just because the vertices have to be a subset of the vertices of the uniform matroid. So this is like a fact that we can use to our advantage to describe the universal valuation, or rather that this is a fact that Dirksen and Fink used when they did this for matroids, but that we also, we're trying to use for the Coxeter setting, which I'll talk about very soon. So people are very interested in matroid valuations because, as I mentioned, these are the functions that behave nicely on subdivisions, and matroid subdivisions have a lot of connections to algebraic geometry. So this is kind of the motivation for looking at this. And also Coxeter matroids, which I'll say in a second what they are like a bit less studied, but they're also like, for example, Felipe Rincon showed that in type D, you can still like have some relationship between Coxeter matroids of type D and elements of the tropical Grassmannian in type D. So Coxeter matroids are starting to have these same kind of applications as well. Okay, so I want to talk about the universal valuation for matroids. So So, and just to clarify, this is like work that was done by Dirksen and Fink that I'm just overviewing. So the universal valuation for matroids, we would hope that since matroids are a subfamily of generalized permutahedra, that I can use this valuation I said before for generalized permutahedra to get a universal valuation for matroids. But there's a problem, which is that yeah, so the problem is that I want to basically express my matroid in terms of the basis for the indicator functions of matroids. And right now this valuation is expressed in terms of like these cones, but these tangent cones of the permutahedron are not matroid polytopes. So this isn't written out the way we would want. But what we can do is since every matroid is contained in the uniform matroid for its rank, we can just intersect both sides of this equation with the uniform matroid. And then that in this case, it does give us a universal valuation for matroids. Because so in order for that to work, we would need to show that the intersection of one of these cones on the right hand side with the uniform matroid again gives you a matroid polytope. And it turns out that it does, and these are called the Schubert matroids, which I guess since I'm sort of running out of time, I won't spend too much time talking about them, but you get this nice family of matroid polytopes called Schubert matroids. And so Dirksen and Fink were able to show that that the universal valuative matroid invariant is given by taking a formal sum over all Schubert matroids such that some orbit of that Schubert matroid or something in the orbit of that Schubert matroid under the symmetric group action contains your matroid polytope M. And this is obtained exactly in the way, like using the reasoning I was just saying of like intersecting everything with the uniform matroid. So we wanted to generalize this to Coxeter matroids. So here's kind of, this is maybe like not the most standard way to define Coxeter matroids, but it sort of works for what I'm talking about. So now we're thinking that we have some root system phi. So we have our roots R and our reflection group W. And we also have some special vectors called fundamental weights, which I alluded to earlier. And so we're going to define first a uniform Coxeter matroid of a certain rank. And the rank is going to correspond to some choice of fundamental weight. So to get the uniform Coxeter matroid, I'm going to pick one of these special fundamental weights. I'm going to take the orbit under the reflection group and take the convex hull. And that gives me the uniform matroid for that weight. So in type A, the fundamental weights are the vectors like E1, E1 plus E2, E1 plus E2 plus E3, and so on. And so you can see that in type A, choosing one of these fundamental weights amounts to choosing like the rank of my matroid, how many ones and how many zeros will appear in each vertex. So that's kind of how this is analogous to that. So then to define a Coxeter matroid in general, I'm going to say that its vertices have to be a subset of the vertices of a uniform Coxeter matroid, and the edge directions have to be in the root system, just like the requirement to be a generalized permutahedron in type A. So here's a couple of examples. On the left, we have a uniform matroid of type B2, and on the right, we have another Coxeter matroid of type B2. And so we wanted to define a universal valuative invariant for these Coxeter matroids. But unfortunately, so in type A, remember Dirksen and Fink were able to just intersect both sides of the valuation for generalized permutahedra with the uniform matroid, and then that resulted in a matroid valuation. But this actually doesn't work in other types. So from before, I told you about our universal valuation for generalized Coxeter permutahedra, but it doesn't work to just take both sides of that and intersect it with the uniform Coxeter matroid, because these things that you get when you intersect these tangent cones with the uniform matroid are not in general Coxeter matroids in other types. So here's an example of this. This polytope with the blue edges is a uniform matroid of type B3 of rank 2, I think. And then what you get when you intersect it with a certain tangent cone of the B3 permutahedron is this red polytope here. And you can see that, first of all, I'm introducing new vertices on the top edge, which were not vertices of the uniform matroid. So that's bad. That means that this red thing is not a Coxeter matroid polytope. And I'm also introducing bad edge directions, like the one right in the foreground is not even a root in the type B3 root system. So this approach of taking intersections of the uniform matroid and these tangent cones just like doesn't work in other types. And so we had to come up with a different technique to prove or to like describe a universal valuation. So it turns out that like an analogous result to Dirksen and Fink's results for type A does hold in other types, but we needed to use different proof techniques to prove it. So we had to sort of detour through zero Hecke algebras in order to prove some property of these things that I'm calling Coxeter Schubert matroids, which are the analog of Schubert matroids in type A. So a Coxeter Schubert matroid is just going to be what you get when you take a fundamental weight of your Coxeter or your root system, and then you choose some element of your reflection group, and then you take the convex hull of all U acting on your fundamental weight, where U is bigger than or equal to your chosen element W in the Bruch order. And that's sort of analogous to what a Schubert matroid is in type A as well. And so then we were able to show that the universal valuative invariant for Coxeter matroids is equal to a formal sum over all of the Coxeter Schubert matroids, such that some like element in the orbit of that polytope, that Schubert matroid polytope, contains your matroid that you're evaluating at. So that was our result. And I think I'm going a little bit over. So I guess here's some applications. So one thing we were able to do is show that this thing called the interlaced polynomial is valuative. So it was known to be an invariant for certain Coxeter matroids, and we were able to write it in terms of our universal valuation. And then Bastidas and Ardila Sanchez both proved that in type A, at least, Dirksen and Fink's universal valuation behaves or like interacts really nicely with this theory of Hofmannoids for generalized permutahedra. And they were able to use that to show that a lot of different functions were valuative. So whenever that theory becomes generalized to other types, which is something that some people are working on now, we expect that our universal valuation would play a similar role in that theory. So yeah, that's all I had. Thank you. Sorry, it was a little fast at the end.
Question from Mariel.
So in the formula that you just wrote, going maybe related to William's question, so the number of terms is the number of elements in W, or only the ones that are below in the for your universal? What? It's
going to be the number of elements. Yeah, it's going to be the number of elements in the file group. Yeah. Mm-hmm. Yeah, so in type A, you can see this because, let me go back to, yeah, so in type A, you can see this because basically each element of the symmetric group gives you a vertex of the permutahedron. And so then you can take the tangent cone at that vertex and intersect it with the uniform matroid, and that gives you a Schubert matroid. And those are all the ones that appear in this sum. And actually, I didn't really say this, but here I'm taking valuative invariance, so I'm like doing everything up to isomorphism, but yeah, but you still, yeah, so you get n factorial terms in type A and however many are in your Weil group in other types. Yeah.
Any other questions?
Is there a simple example of something that satisfies the weaker version of valuation, but not the strong one?
That's a really good question. I think, I mean, there very well might be, but I feel not prepared to talk about that. So I don't know off the top of my head, but that's a really good question. Yeah.
In your commutative diagram, could you briefly talk about how you prove that phi is unique?
Yeah. So I think it just has to do, like, it's almost, so it just has to do with the fact that, like, if you want to have a, or sorry, so a valuation is the same as a z-linear function. And to write down a z-linear function, all I need to do is find a basis and sort of assign a value to each element of the basis. And so that's, I think this diagram is almost like overkill for saying because really all I'm saying is, like, the F part, like the big arcing arrow, is like write it out in terms of a basis, and then the phi is like assign the appropriate value to each element of the basis. So it's just kind of like implicit in what it means to be a z-linear function. Yeah.
Thank you.
Any other questions?
I just wanted to ask, I'm not sure if we have enough time. I was surprised that the zero Hecke algebras appeared at the end. Do you want to, like, maybe say one more word about how they're used in your proof?
Yeah, so we needed to show, so we had these Coxeter Schubert matroids, and we kind of, like, we knew we wanted that to give us the universal valuation because it was kind of analogous to type A. But we needed to show, I think, that they were spanning, I think was the part that we used it for. So yeah, I'm not sure if I could say very much about the details, like, off the top of my head, but basically we needed this in order to, like, we needed to use some like machinery from that in order to prove that these Schubert matroids were spanning. Yeah.
No, that's cool. Thank you. It's really nice.
Well, if there are no more questions, then we thank Mariel again. Thank you for your talk.